Okay, so I have just 10 o'clock here, so I think we'll go ahead and get started. I want to thank everybody for joining us today for this weekly webinar. So our topic today is just going to be to cover some of the basics of generator protection, and we're going to focus on primarily medium voltage generators and what the typical protection recommendations are, and how that to some extent depends on your interconnection and also on how the system is grounded. So we'll look at some examples of different types of connections and just kind of discuss the basic protection requirements. At the end, I'll give you a couple of references. If you're getting into this in more detail, you may want to look into those as well. So like everything else, the protection that you put on your generator depends on the generator size, how it's interconnected to the system, the interconnection requirements imposed by the utility or the regional grid, how the generator is grounded, the importance of the generator to your system or to your operation, and always what your budget is and how much you're willing to spend. So in terms of electrical protection for the generator, we can kind of break it down into two broad categories. There's always going to be a little bit of overlap here, but basically we're going to think about internal faults inside the generator and to some extent within the generator protection zone, which may extend beyond the generator a little ways. And then we'll look at external faults and backup protection for those, and then abnormal operating conditions that we need to protect the machine against. So if you have a large generator in your system, that's a major investment. It's a long lead item, and so if you're going to have damage to the equipment or to the generator, you want to minimize that to the extent possible. And ideally, if you have a winding fault, you want to be able to just replace that winding and not have to restack the stator core due to a lot of damage to the core. So those are the goals. So if we start talking about internal faults, primarily we're talking about stator faults inside the machine. But when we have differential protection, that differential zone's typically going to extend beyond the machine itself. So we will include anything within the differential zone and the ground fault in that area as an internal fault. So this would also include rotor ground faults and also loss of excitation, loss of field. And we'll discuss those. So those are the typical internal faults or conditions that we're trying to protect against. As far as the typical abnormal conditions that we try to protect against for the generator, generator motoring, sometimes or reverse power, low forward power, those names are all somewhat interchangeable. The 32 is the ANSI function code that you'll see used for this. So we'll talk about why the generator motoring or reverse power is something we want to monitor. Over voltage and or volts per hertz, under voltage, negative sequence current is related to imbalance or phase-to-phase faults, and that can be particularly damaging to the rotor of a synchronous machine. Overloading of the generator, and then over and under frequency. And we'll look at how we protect against those and why it's a concern. When you get into over and under frequency, sometimes the interconnection requirements that are imposed on you by the utility or the grid will become the dominant issue there to deal with. So there will be some overlap between the generator protection and your interconnection requirements. So in general, the type of protection we use depends to some extent on how the generator is connected to the system. And the two main categories we're going to talk about are what we call unit connected or direct connected. And that's going to depend a little bit on the size and the nature of the generating facility. So if we talk about unit connected, these are typically large utility generating facilities or large cogeneration facilities, with the key word there being large. And the basic principle, what defines a unit connected generator, is that each generator has a dedicated step-up transformer, and that's going to be a delta Y. So that's going to isolate the generator ground from the system ground. That gives us much better protection, much limits the probability of having to deal with system grounds that can affect the generator. We'll also have, on a large power plant, you're typically going to have some kind of unit auxiliary transformer that comes off the same bus. And high resistance grounding is the norm here. There's really no reason not to use high resistance grounding, and a lot of advantages to it to limit the ground fault current. And with the unit connected concept, we can have multiple units at the same facility. We just keep adding them on, each with its own step-up transformer and unit auxiliary transformer. So here's an example of a unit connected generating facility. Just a little EasyPower one line here. So here's my generator, and out here is my substation, 230 kV, and this is going to be my connection to the outside world, where my power gets exported out to the grid. Then off of the generator bus, we have a second transformer that goes 13.8 to 4160. That's station service. It serves the house loads for this power plant. And so the key thing here is that these transformers are dedicated to this one particular generator, and so there's no direct connection from the generator to the rest of the system. All the connections go through these transformers. And because these transformers are delta Y, when I have ground faults out on my system, they do not appear as ground faults to the generator. So it makes it much easier to provide ground fault protection. As I mentioned, we're normally going to have a high resistance grounding here via a distribution transformer, just to get the turns ratio advantage and allow me to put in a smaller resistor. So we're going to limit that ground fault current to something in the range of 5 amps on a high resistance grounded system, and that's kind of a whole topic in itself. Basically, you're going to make it as low as possible while limiting the overvoltage transients that can occur. So something in the range of 5 amps is going to be typical. Okay, so that's the unit connected. So typically these are going to be large generators. The other option I mentioned was direct connected. This is going to be more typical of industrial facilities, cogeneration plants, and smaller utility plants. You have small isolated utility systems on islands. You may have lots of diesel generator systems, and these are typically going to be direct connected. So the key here is that generators are connected direct to a common generator bus, each one with its own breaker, and then loads are served directly from that bus or through a common transformer. So these are generally going to be low resistance grounded. And that allows us, helps protect the machine, but also allows sufficient ground fault current that we can selectively coordinate faults in the system. So here's just a simple example of direct connected generators. I have 3 units, each of them 10 MVA, 4160, and each one has a generator breaker. So we would synchronize across this breaker to a common bus, and then typically, not always, but you oftentimes will have some kind of a transformer here to interface out to the utility system or to the grid, and then another breaker that's going to feed your local loads, plant loads, directly. So so the difference here is I don't have the transformer for each generator to isolate it from the rest of the system. So there is interaction between the generators and the rest of the system, particularly for ground faults. It's significantly different. So in these situations, we normally would use what we call low resistance grounding, and that's going to limit the current to something between 50 amps and 1,000 amps. That's kind of the range for what we define as low resistance grounding. So this is be a direct connected, and again, I can have more than as many units as I need here. All right, so if we look at the typical protection schemes we're trying to provide here, the first one we're going to talk about are phase faults. So phase faults in the generator is relatively rare, but if you do have one, it can cause major damage. So we want to try to trip as fast as we possibly can. And so for any generator probably over about 1 MVA, you should be looking at some type of differential protection if at all possible. And the advantage here is that I don't have to coordinate that with anything, because if the differential element operates, I know the fault is within the generator or the generator differential zone, and I can trip quickly. And these are extremely fast and can trip off the line within a cycle or so. The only downside to the differential protection is that when I have resistance grounding, the differential protection is not always going to detect all those ground faults. So we need a different type of protection there, and we'll take a look at that. And for high resistance grounding, it becomes a little more difficult to make sure we detect all the ground faults. So for phase faults within the machine, the differential is our primary source of protection, and that's the preferred method. So here's just a typical scheme if you're not familiar with differentials. So this is the 3 generator leads going out to my system. This is the neutral side. These are brought out to a common neutral point here, tied together, but I have these CTs here as well. So the current going in and out here have to be equal. So we sum those each current in each phase. There's a restraining coil or signal, and then these are the operate coils. So if we have a difference in current, that indicates there's current going somewhere that we don't want it to go, and there's a fault, and we can trip. So these are extremely sensitive and well worth the effort to get the extra connections and the CTs here. So in addition to the differential protection, that's our primary phase fault protection for the machine, we also need some kind of backup in case for whatever reason that doesn't pick up the fault. Also, if we have a fault that's outside of the differential zone, and that's ideally that's going to get cleared by some other protective device, but if it doesn't, we need a backup to allow the generator to trip offline to protect itself. So this is complicated by the fact that if you look, and we'll have some slides on this, but when I have a fault that the generator is feeding current into, the current out of the generator is not constant. It decays over time, depending on the exciter and other configurations. But we have to account for the fact that over time that current can decay significantly. And so instead of a standard overcurrent relay, we typically use what we call a 51V, which is either going to be voltage controlled or voltage restrained. And they both are trying to accomplish the same thing. Basically, it allows us to have an overcurrent element that will actually pick up below the full load current of the machine if the voltage goes low enough. So on a voltage controlled relay, you essentially block the overcurrent function until the voltage drops below some set point value, and then the overcurrent relay will operate on whatever curve it's set on. The voltage restrained is more complicated. Depending on the voltage, the curve will actually shift, the time current curve for the overcurrent. So the lower the voltage, the more sensitive the overcurrent relay becomes. So the reason for all of this is the way the generator behaves during a fault. So here's a generator decrement curve that shows how the fault current behaves as the fault proceeds. So this is a time current curve. You can produce these in EasyPower in the coordination focus if you have the generator impedances and the time constants. So this is where we get into the subtransient reactance, the transient reactance, which is X prime, and the synchronous reactance, along with the time constants. So on the time current curve, time is going up vertically. So in the beginning, my fault current's quite high, but it immediately starts to decay. I get into the subtransient region, and then eventually it decays down to the synchronous reactance. Many times the synchronous reactance is going to be over 100%, and that means that the sustained fault current is going to be less than the full load current. Now this curve assumes a constant excitation. In the real world, you may have some type of field forcing, which is going to drive the fault current somewhat higher than this. So this curve will look the same, but it's going to drop down this way. Instead of going all the way down, it'll be higher. And we can take a look at that in EasyPower here. In fact, we'll go ahead and do that now. Let me jump. So I have, this is our direct connected system here. If I go to coordination focus, if I look just at this generator, I go to plot, I get the curve we were just looking at basically. And so that data is contained in the TCC tab. So if I double click on the generator, there's a TCC tab for every generator. And the subtransient, transient is going to pull that out of the data in the specifications tab that you've already entered, this data. You'll have to add the XD, which is the synchronous reactance, and the time constants. This you'll have to get from the manufacturer's data sheet or test reports. So the curve that's plotted here represents the generator fault current output without field forcing. In other words, the excitation into the machine remains constant during the fault. If your generator has what we call field forcing, when the current starts to decay and there's a fault, the voltage regulator, the excitation system, will go put additional current into the field to keep the voltage up basically, and drive more current into the fault. And so if I select with field forcing, then I can define what the level of field forcing is. In this case, I've got 3 per unit, 300%, it's pretty common. So when I apply this, you see I get a second curve. So this is with constant excitation, this is with the field forcing. So this is the difference that makes. So the field forcing helps in terms of detecting faults and clearing faults. Okay. So let me get back to PowerPoint. So this is the generator fault decrement curve. And so because of this characteristic, we have to make sure we can actually detect a fault that's sustained for a long time, and that's where the voltage controlled overcurrent relays come into play. All right, so another common protection that you need to apply to these generators is negative sequence overcurrent protection. So anytime we have an imbalanced voltages, imbalanced loads, we have negative sequence currents. If you're familiar with symmetrical component theory, there will be negative sequence currents for any imbalance, whether it's a load or a fault. The worst case scenario we're dealing with would be a phase-to-phase fault in the machine. And that's going to generate huge value of negative sequence current. Now, negative sequence currents are basically in a reverse phase rotation, phase sequence from the normal power system. So it's like if your normal phase sequence is ABC, the negative sequence current is going to be ACB. And so if you look at a rotor that's spinning at synchronous speed, this negative sequence current actually appears as a double frequency. So on a 60 Hertz system, that's going to look like 120 Hertz when it gets to the rotor. So these currents do create flux that crosses the air gap and induces current in the rotor. And at 120 Hertz, the higher frequency, that current tends to stay on the surface of the rotor and can be extremely damaging to the rotor. So we have the manufacturer of the generator should give you limits on the maximum negative sequence current and for the amount of time that it can withstand. And this is how we set our negative sequence overcurrent elements. So typically the continuous, so anytime you have any imbalance, you have negative sequence currents. So they have to be able to withstand some amount of negative sequence current. And that's limited to about 10%. Once you get over that, then you'll start to alarm, and then above a certain other value. So it's kind of an I squared T function. So it's a heating issue. So there'll be limits that are provided. In the IEEE guides, they have some recommendations for different types of machines, but ideally you would get this from the manufacturer. So you can use inverse time curves similar to normal phase overcurrent, or you can use some kind of a definite time where it's above a certain value for a certain amount of time it's going to trip. So this provides, so there's usually two levels of protection that you're going to provide. One is for these kind of long-term imbalance issues, and the other is to detect imbalance faults that's going to really provide backup to your other protection. So negative sequence is very important because of the sensitivity of the generator to negative sequence currents, particularly the issues in the rotor. But the other kind of abnormal operating condition we're going to deal with is loss of field, loss of excitation. So if you have a machine that's running at full load and you suddenly lose the field, it loses all of its restraining torque and it'll quickly go to overspeed. If you have issues that can cause it to slip poles, lose synchronism, those kinds of issues can be very damaging to the generator. So normally these days the excitation system is going to provide protection against loss of field. It's built into the excitation system, but you need a separate relay, protective relay to back up the excitation system. So that's going to be the loss of field protection. Typically what we do these days is use a distance type protective element that looks at the R and X that it sees. So we need a voltage and current input for loss of field. And we do this by taking the capability curve of the generator and converting that to a RX diagram. So let's take a look at just a typical generator capability curve. So the vertical axis here is the reactive power, and the horizontal axis is the real power. So we're just sticking to these two quadrants. We're not looking at if we were on this side, this is when the generator is motoring or reverse power. But looking at the situation, this basically defines the region that the unit can operate at. So up in this quadrant, this is real power into the system and reactive power into the system. So I've got VARs and megawatts going into the system. We call this is normal overexcited operation. This is lagging. The generator is lagging when it's providing VARs into the system. And these are the limits This is due to stator winding. Above this point, you're into the limiting to the rotor heating, and then you get into overexcitation limits here as your bars start going too high. In this quadrant below, we're underexcited, so we're still delivering power into the system, but the unit is absorbing VARs into the generator. And this has more limitations and more concerns. If we get too far underexcited, we can lose synchronism or slip a pole and those kind of things. But generally, underexcited means we have megawatts power going into the system, but VARs going into the generator. This is, in this situation, the generator is leading, operating in a leading power factor. So in order to monitor loss of field, we take this generator capability curve. Basically, this is power and this is Q or VARs. We convert this to an RX diagram, and this defines the operating. Basically, this is the conversion of that curve into an RX diagram. So my generator needs to operate outside of this region here. So once we've defined that region, we can set the distance elements. We typically use 2. So these are offset Mo elements, and these are going to be built into your relay typically. This is for loss of field again. This first element is going to have some kind of time delay. So what happens is if combination of R and X that's seen by the generator gets into this region, it's going to trip. So as we have transients, we can briefly maybe tip into this circle, so we want to put a time delay, 1/10 of a second, something like that, on this outer circle. The inner circle will trip basically instantaneously. So this is the typical protection that we use to detect loss of field, under excitation type of issues. And if you are trying to apply this, the relay instruction book will generally give you some guidelines for setting this. It's usually a function of the transient reactance and the synchronous reactance. All right, so we typically are going to want reverse power protection on our generating units. And reverse power does not mean the generator is going backwards. It means that it's not producing real power. We're out of those 2 quadrants or into the other quadrants where the power is going into the generator. And the generator basically becomes a motor, a synchronous motor. Now, the reality is that this reverse power protection is provided to protect the prime mover, not necessarily the generator. The generator is happy operating as a motor within certain excitation limits, but reverse power can cause major problems for steam turbines, gas turbines, reciprocating engines, hydropower units. So the reverse power is really there to protect the prime mover and not the generator. For steam turbines, when I have low power, I can get overheating in the low pressure sections of the turbine because the turbine depends on steam flow to cool that low section as steam goes into the condenser. So these reverse power settings are very low compared to the actual normal rating of the generator, so 1% to 3%. So it becomes an accuracy issue when I have CTs and PTs that are sized for the normal full power, and I'm trying to monitor real power down in the 1% to 3% of the full power. So the accuracy becomes a little bit of an issue, but there will be guidelines for reverse power for whatever type of prime mover that you have. For reciprocating engines, there's risks of damage to the engine in explosions and gas turbines and that kind of thing. So it's important to understand the limits for reverse power based on the particular prime mover that you have. In steam turbines, it's also common these days to use reverse power for normal shutdown, and that's to verify that the steam valves have actually closed. Historically, there's been a lot of cases where the indication said the steam valves were closed and they were not closed, and as soon as the field was removed, the generator went into overspeed and self-destructed. So it's common now to use reverse power to prove that the steam valves have closed. So that's another use for reverse power. Volts per Hertz protection is really to prevent against excessive voltage, high flux, and saturation of the core, and that can be extremely damaging. In addition to volts per Hertz, you need standard over voltage protection. Again, as with we mentioned with the excitation system, the voltage regulator should provide protection against volts per Hertz and over voltage, under voltage, but the protected relay will be used as a backup to the voltage regulator. Over voltage settings may also be dictated by your transmission operator or your power, your utility, and so that's another factor that you have to put in there. Generator overloading or overheating, the best protection there is really going to be embedded RTDs, temperature detectors in the stator, and to provide alarm and tripping for those. And if you have water-cooled stator or hydrogen cooling, you're going to need some runbacks, automatic load reductions or trips if you lose those modes of cooling. Now, if you don't have RTDs, the relays these days can typically provide a thermal model similar to what we do with motor protection. So that would be another option, although the actual temperature measurements are going to be your best protection against actual overloading or overheating of the windings. All right, some other protection you may run into, and that's typically provided as an option or built into a lot of the new multifunction relays, some kind of distance protection as a backup phase fault detection. And this is going to be similar to the voltage restrained relays that we talked about, but you just use a distance element looking back up into the system to detect faults. Over under frequency, again, this is going to be tied to your volts per Hertz, but also your interconnection requirements. But obviously there's going to be limitations on the frequency range that this system can operate at, but normally your grid requirements are going to be more severe than the actual machine limitations. Inadvertent energization, this will be a case of somehow the generator breaker closed and the unit was not running. That's obviously not a good situation. So you can typically detect that and trip on that very quickly. Sync check protection is to provide backup to your automatic synchronizer or your manual synchronizing, just to make sure that's not being closed in grossly out of sync. And then as a stability issue for very large generators, you may need to provide out-of-step protection, but that would generally be dictated by your grid operator. Okay, so let's talk now about ground protection, ground fault protection, and before we do that, we need to talk about methods for generator grounding. And if we're talking about medium voltage generators, the recommendations of the IEEE and pretty much anyone else is going to be that you use some type of resistance grounding on the neutral of the generator. Solidly grounded generators are typically not recommended if you can avoid it. So some situations may be necessary to provide ground source, but normally you're going to want to avoid solidly grounding the generator. And the reason is that the ground faults are going to be the most common fault, and so you can limit the damage by reducing the ground fault current. Also, if you look at the impedances for most generators, the zero sequence impedance is going to be lower than the subtransient reactance, so that means that the ground for a line to ground fault, the fault current can actually be higher than the three-phase fault currents, and that's going to cause can cause severe stator core damage. So the ground fault protection that we use is going to depend on the grounding method. So we'll talk just briefly about that. Again, this could be a whole topic in itself, but we mentioned that for direct connected generators, we're typically going to use low resistance grounding, and through some kind of a resistor, we're going to limit the ground fault current to something between 50 amps to 1,000 amps. So that's a pretty big range. The lower the better, but traditionally we used higher values when we had electromechanical relays. Now with the newer relays that are more sensitive, you can probably go to something lower, 200 amps, 100 amps, maybe all the way down to 50 amps. Now the low resistance grounding does limit the damage, but even at 100 amps, 200 amps, there's still a fair amount of damage that can be done. But the advantage is that if I have 200 amps, 200 amp resistor, let's say, with 200 amps flowing, I can use my normal overcurrent relays, ground overcurrent relays, to detect that and to selectively coordinate. So on a direct connected generator where I've got other plant loads and other plant switchgear and relaying, I can coordinate those so I maintain selectivity. With high resistance grounding, that's not easy to do, but low resistance grounding, it's fairly easy to achieve. The trade-off is you're going to have more damage when you do have a fault in the stator core. Okay. So here's our typical direct connected system. I've got 3 generators. Each has its own grounding resistor. That's commonly done in the United States. Connected to a common bus. And so when I have a ground fault, if I have a ground fault out of my system somewhere, that's going to limit the ground fault current that this generator can provide to 100 amps. But I'll get 100 amps from each generator, so those will add up out here. And we'll talk about this in a minute. If I have a grounded Y here on my step-up transformer to the utility, then this is going to contribute a huge amount of fault current. So you have to watch out for this. And we'll do an example here in a minute to show you how much difference this makes. So if you're going to have low resistance grounding, you want every ground source to be resistance grounded. All right, so the other thing you have to be concerned of in this situation where I have multiple generators on a common bus is going to be circulating currents. So you've probably heard that all the generators need to have the same pitch, and that relates to the harmonics that the generator generates. So if I have some kind of harmonic voltage present that can force current through my ground, things like third harmonics are going to look like zero sequence currents. And so I have an issue with current going through this resistor. It might only have a 10-second rating for faults. So if I have a certain amount of third harmonic current, I have to be concerned about if these resistors are going to be adequately rated and they can dissipate the heat on a continuous basis. With the low resistance grounding, I'm typically going to have some kind of an overcurrent relay here, and that's going to be used to trip off the generator, and hopefully something out here will trip first depending on where the fault is. All right, let's take a quick look at my system here. I've got if I go to short circuit focus, I have each one of these generators is grounded through a 100 amp resistor, and I've got my transformer here. Let me take a look. And I have a 100 amp resistor in the transformer neutral. So if I switch to line to ground faults, I'm going to fault the generator bus here just by double clicking on it. So I get a total fault current of 400 amps. So that's basically 100 amps from each one of these sources through its 100 amp resistor. And I can see that if I switch, instead of looking at A phase current, if I look at the 3I0, I'm going to see 100 amps ground current from each source. Okay, so that looks reasonable. So I get a total of 400 amps. So if this fault, instead of being on the generator bus, was actually in the generator, I would have essentially 400 amps of ground fault current flowing into this generator. Even though this resistor is 100 amps, the total ground fault current, the total energy is going to be based on the 400 amps. So as you add units and ground sources, you have more and more fault current. So the alternative is to have a common resistor, one grounded resistor where you might have to switch the ones that you're not going to be in service, and you do see that done in some parts of the world. It's not common in the US. It creates operational issues because you have to remember to make sure you have the right resistor in the circuit. But just remember that just because I have 100 amps here in my resistor doesn't mean this fault current is going to be limited to 100 amps if the fault's in the generator. Alright, so if I go back to database, let's take a look. If I were to get rid of this grounding resistor and go to solid grounding, so now I have a solidly grounded Y here, and this is a delta. So this is going to be a ground source for my 4160 volt system here. So now when I go back to short circuit, on line to ground, when I do a fault this bus, now instead of 400 amps, I get 63,000 amps. And the phase current here is much greater. So if I were to have a ground fault within my generator, I'm going to have a huge amount of fault current flowing into that machine that's going to cause significant damage because this is solidly grounded. So to really protect your machines, you need to have every ground source resistance grounded. Okay. All right, so let's go back to my PowerPoint here. So again, beware of these solidly grounded transformer neutrals. Okay, so that was low resistance grounding. Let's talk about high resistance grounding. Concept is the same. We're going to put some impedance between the neutral and ground to limit the fault current, but we're going to go to a much higher resistance. And so we're going to limit the current to something around 5 amps, maybe less. The idea is to roughly equal the capacitive reactance of the system. And this is, again, another topic in itself, but what we're trying to do is minimize the over voltage that can occur during a fault and limiting the current to the extent that we can. So we're going to go from something, let's say 200 amps down to 5 amps, so we greatly reduce the damage that can occur in the machine. But we have so little current, say we have 4 or 5 amps of fault current, very difficult to use a normal overcurrent relay to detect that. So what we do is we use a voltage. So the normal scheme here is we're going to ground this through some type of usually just a single phase distribution transformer. And this will be, if it's a 4160 volt generator, this is going to be 2400 volts here and 120 or 240 here. And so the resistor, basically, the resistance value is multiplied by the square of this turns ratio. So I can get by with a much smaller resistor by doing it this way. So the normal scheme is to put a over voltage relay here, that when I do get a ground fault, I get a voltage that appears across the resistor, and then I trip on the voltage. And that works fine, but the problem is there's no way to tell where the fault is on the system. So this is going to operate for a ground fault anywhere on that system. So it's not, selective coordination is extremely difficult, if not impossible. So this is typically used, that's another advantage of the unit connected generators. So if we go back, and I thought I had a slider. Well, let me go back. One more. On the unit connected generators, we had the unit transformer that isolated the generator from the rest of the system. So using high resistance ground, I'm not really giving up any selectivity, because for a fault anywhere in the generator through the transformer, I'm going to want to trip anyway. So this is ideal for unit connected generators, and that's one of the big advantages of the unit connected generators. So let me just go here. So here's my unit connected generator, my high resistance grounding. So any ground fault down through the delta windings here is going to show up. I'm going to have voltage across my voltage sensing, and it's going to trip. Okay. So if the fault is down here on the Y side, it's not going to appear as a ground fault here. So this ground relay will not see that fault. Okay. That's the advantage of the unit transformer, unit generator concept. All right, so if we think about a normal Y-connected generator, if I have a ground fault in a winding that's very close to the neutral point, I have a lot less voltage there. So those are much, much harder to detect. And so with the high resistance grounding, there's a limit to what we're going to be able to detect. And so there's a lot of schemes that have been developed to provide what they call 100% stator ground fault detection. So for the very large machines, this becomes an issue. But I'm not going to get into all the details of all the different approaches that have been taken, but just be aware that there will be a limit. If I'm just using my normal high resistance grounding and voltage detection, there will be a limit. You might only get 90% of the stator winding for ground fault protection. You got to think about the part that you're not really going to be able to detect. But there are schemes that try to do that. All right, so just wanted to touch briefly on the distinction between generator protection and interconnection protection. There is some overlap, and if I only have one generator, then essentially it all can kind of meld together. But when I have multiple generators with a common connection to the grid, I'm going to have individual generator protection, plus I'm going to have some type of interconnection protection. So those are typically going to be different relays. Don't have to be, but the utility or the transmission operator is going to provide rules and guidelines as far as your interconnection protection. So as far as the actual generator protection, that's more the responsibility of whoever owns the generator. So just keep in mind that those are related, but they're not necessarily going to be the same protection. All right, just to get down to the issue of what relay should I buy, there's lots of relays out there right now that can provide generator protection, and so you're going to want to get some type of microprocessor or multifunction relay. So I can buy a single relay. This is a Schweitzer 300G, but there's other similar products available from other suppliers. That one relay can provide all of the protective functions and a lot of the interconnection requirements. So all the functions we talked about today can all be provided in this one box, provided you have the right CT and PT inputs into it. However, if this relay should happen to fail, and they definitely can, you go from having wonderful protection to having absolutely no protection. So you're going to want some type of backup in a separate relay. Some people will just duplicate these two relays, have identical relays with identical settings, and that's fine. Or you may go to something a little less elaborate, but you're going to need a separate relay that can provide some backup protection. So ideally you would have your backup relay would connect to a separate set of CTs in case the CT fails, but one way or the other you do really want to have a backup relay of some type. All right, so suggested references if you want more information. The kind of the Bible that we go by is the IEEE Guide for AC Generator Protection, C37102. As far as a text, if you're interested at all in protection or protective relaying, I would recommend the Protective Relaying book by Blackburn, J. Lewis Blackburn. And I'm sure if you go to search for this at Amazon, you'll find it. So. I have a lot of questions here and our time is about up, so let me see if I can run through some of these, but if I don't get to your question or you have additional questions, just please email me here at david@easypower.com and I will get back to you. So if I don't get to your question right now, I apologize, but feel free to email me your questions. And we kind of just touched on this, and I haven't provided a tremendous amount of specifics, but that's going to depend on your particular application and installation. So hopefully this kind of at least gets you pointed in the right direction. I'll take a couple questions here. There's a question about solar farm requiring reverse power protection. I don't think that would be an issue, although it would be probably a function that's provided in the interconnection relay. But they don't have the same, as we mentioned, the reverse power is an issue for the prime mover. We're talking about synchronous generators here for the most part today. Set point for the negative sequence current, that's going to depend on the generator, and there should be guidelines provided by the generator supplier. In the IEEE guide, there are also recommendations. The value of resistance to the ground should be the same. So determining the value for the grounding resistor and what to limit the current to is somewhat of an art. I mean, theoretically, you're supposed to limit, for high resistance grounding, you would limit it to, you would size the resistance the same as the capacitive reactance of the system, which is difficult to calculate because it's hard to get that data, but there's some guidelines. But it's not going to be that precise, but you're going to end up something in the range of 3 to 5 amps for most systems. If the resistance is too high and the current's too low, your transient over voltages can go high. If the resistance is too low and the current is lower and the current is higher, you just have more damage that's going to occur just based on the I squared T function. So for low resistance there, that's really just a question of being able to, you want it as low as possible and still be able to selectively coordinate. So if I only have 2 relays I'm trying to coordinate, I could probably get by with 50 amps. If I got 4 levels of overcurrent relays I'm trying to coordinate, I'm going to need more current to be able to reliably coordinate those. So someone asked about a recording. I am recording this, I hope, and that recording will be posted on the EasyPower website here once they get it converted and posted. It'll take a few days probably, but it will get posted. It's a question about the modeling of these relays in EasyPower, and yeah, a lot of what we've been talking about cannot be explicitly modeled in the short circuit or in the coordination module of EasyPower at this point anyway. So we're kind of limited to overcurrent devices, phase and ground. If you, in the dynamic stability module, we can simulate the response of the generator in terms of voltage and frequency. And you can have voltage relays and frequency relays modeled in dynamic stability. So if you're looking for more of a dynamic transient analysis and dynamic stability, you can do that provided you have enough data regarding the generator characteristics, the exciter, the governor, and the system itself. So if you have dynamic stability, there's a much greater capability to accurately model the response of the generator to any abnormal condition, including faults. So yeah, I think there is somebody pointed out, I think I have the wrong version here. There is a newer version of C37102 that's going to include there's a hybrid grounding method that they're recommending that is kind of a combination of low resistance grounding and high resistance grounding. So that's a kind of I was trying to avoid getting into that. It's somewhat complicated to explain, but basically combines the elements of high resistance grounding and low resistance grounding. And so for new systems, that's something you might want to take a look at. So this says 1987, but I believe there's a later version that's now available. So if you buy it, I'm sure you'll get the latest one. All right, so our time is up. I want to thank everybody for joining us today, and stay tuned. We'll have additional webinars down the road, and hope to talk to you again in the future. So again, email me if you have specific questions or comments. Thanks everybody, and we'll talk to you again soon.